So 2.4 deals with the chain rule. The chain rule allows us to take the derivative of more complicated functions, functions that are really compositions of functions. Okay, so when we look at the notation for this, we say that if we want the derivative of this composite function f of g of x, all right, the notation can be a little confusing, but look at what we're really doing here. If we think about this as an outer part, the f function is the outer part, and the inner function is this g of x. So in order to take the derivative of this composite function, we're going to take the derivative of the outer part, so f prime, without changing the inner part at all, and then multiply by the derivative of that inner part. And when we do that, that's going to give us the overall derivative of this composite function. All right, so basically we're going to work from the outside and move in as we go. All right, so we're going to look at some examples. First example looks like this. It's the quantity 4x cubed plus 6x all cubed. So this is really a composite function because you have something cubed. That's the outer kind of outer function, and then the inner function is this 4x cubed plus 6x. All right, so in following this pattern above, we have the derivative of the outer part with the inner part unchanged times the derivative of the inner part. So I'm going to take the derivative of this outer part, which is something cubed. So we're going to use the power rule on that. So we go, okay, well that's going to be 3 times that same quantity squared. That's the power rule. Times the derivative of the inner part here. We're going to use the power rule here as well. We get 3 times 4 is 12x squared plus 6. And we really have taken the derivative there, right? We're done with the derivative. Everything that we do from here on out to this problem, from here on out to this problem is really just cleaning this up and making it look nicer. So we've taken the derivative. That's the chain rule applied to f of x, right? So if I look at this first part here, I'm going to factor out a 3 and a 2x squared. And then this part here, I'm going to factor the 6 out. And I'm going to rearrange those. So I have the 2x squared plus 3 squared, the 2x squared plus 1, and then the 3 times 6 times the quantity 2x squared gives me the 72x squared. Alright, so again, this is the derivative. This is the chain rule here. The rest of this is just cleaning this up a little bit so that it has those 3 kind of neat factors. The next problem, we have the cubed root of the quantity 3x squared minus 1 squared. And the very first thing that I'm going to do here is I'm going to write this, rather than as a root, I'm going to write it as a rational exponent. So that's 3x squared minus 1, all to the power of 2/3. All right, so I have the outer part of this function is this quantity to the 2/3 power, and the inner part is the 3x squared minus 1. So the derivative of the outer part, we're going to multiply the 2/3 down and subtract 1 from the exponent. The inner part remains unchanged. And then the derivative of the inner part is just going to be 6x, so I multiply by 6x. That's my g prime. And so again, I have the derivative. I'm going to clean that up a little bit. I have the 6 and the 3 reduced to a 2. The 2 multiplies by that 2, I get a 4. Here's the x. And then this quantity to the negative 1/3 is really the cube root down in the denominator. All right, the next one is a trigonometric function. So we have to talk a little bit about the notation here. Notice that it's cosine squared of 5x. So this is really cosine of 5x times cosine of 5x, right? It's the cosine function itself that's really squared, and we usually will see it written this way, but we can think about this as the cosine of 5x squared. Okay, and so when we think about it this way, if we see this, I almost want you to kind of visualize it this way. I think that it's easier to think about this as a composite function. That way, it's easier to imagine there's an inner part, which is the cosine of 5x, and there's an outer part, which is this quantity squared. Okay, and in fact, this composite function really has three parts. So let's work from the outside in. We have this quantity squared. We have the cosine, which is sort of the middle function, the middle layer, and then the innermost layer is just this 5x. Okay, so in this case we have really three layers to work with. So we're going to start from the outside in. I have a quantity squared, so I would take the derivative of that by saying multiplying the 2 in front and subtracting 1 from the exponent with the inside remaining unchanged. So I have 2 times cosine of 5x now to the first power. Now the derivative of the cosine of 5x, the derivative of cosine is negative sine. So now I'm multiplying by negative sine of 5x. Again, this inner part remains unchanged. And then finally I multiply by the derivative of 5x, which is 5. So there's my derivative. Again, this final step is just cleaning this up. So I have the 2 and the negative 1 and the 5 give me a negative 10, and then I have the cosine of 5x and the sine of 5x. Alright, one more trigonometric function. So this one we have tangent of 2x minus 5. So the outer part of this composite function is tangent. The inner part is the 2x minus 5. So the derivative of tangent is secant squared. So we have secant squared of 2x minus 5. The part in the parentheses, or the innermost part of this composite function, is unchanged. And then we multiply by the derivative of the inner part, which is 2. And we have 2 secant squared of 2x minus 5, which is our final derivative. All right, last example. We're given this function, f of x, that's 1 over the quantity x squared minus 3x squared. And in this case, they ask us to evaluate the derivative at a specific point, at the point 4 comma 1 over 16. Okay, so really we're just going to do the same thing we did for the last problems. We're going to find f prime, and then we're going to substitute 4 in to find f prime of 4. So again, I start out, I want to write this just as a power. So rather than 1 over this quantity squared, I rewrite it as that quantity to the negative 2. And here again I have a composite function. The inner part is x squared minus 3x. The outer part is this quantity to the negative 2. So I'm going to multiply the negative 2 in front and subtract 1 from the exponent. So it becomes negative 2 times that same quantity to the negative 3. Then I multiply by the inner part of that, by the derivative of the inner part, and so I get 2x minus 3 there. So when we clean that up, it starts to look like that. Alright, now we say, okay, well, what's f prime of 4? This is f prime. F prime of 4 is just, we substitute 4 in for the x, do the arithmetic, simplify, and we get negative 5 over 32. Alright, so really the same process up to here as the previous examples we used, except now we're saying not only do we want to know what the derivative is, but we want to know the derivative specifically at a point or a given x value, and we can find that. So the slope of the tangent line of this graph at x equals 4 is negative 5/32.